If you look at the last two videos, it might not be perfectly clear exactly what we're trying to accomplish here. In the second video of this particular topic, we looked at just some very fundamental building block kind of statements when we looked at the limits of various functions. And then in the previous video, we looked at the algebraic properties of limits. And I told you that this would give us something powerful. And what it actually is going to give us the opportunity to do is a lot of times, as long as a function is well behaved, it doesn't have any irregularities to it, we're going to be able to evaluate limits using the process of direct substitution. And so let's watch this in action. Let's take a look at the function f of x equaling 2x cubed plus 4x minus 5. Now then, in your limits toolbox, if you will, you know two main ideas. We can either graph this function, which we're not going to really be able to do by hand. That's going to require us to use a calculator. Or we can build a table of values, because what we're going to want to find here, I should say, is we're going to look at the limit as x approaches the value 3 of this particular function, 2x cubed plus 4x minus 5. So I can either graph this function and look at what's happening at 3, or I can build a table of values like we did in the previous topic as x is getting really close to 3 and see what's happening with this function. But because nothing weird's happening, we're going to be able to apply these properties here, and we're actually going to be able to do this by hand rather than using a tool that's going to make us grab a calculator. So let's take a look at what we have here. We have a trinomial expression, 2x cubed plus 4x minus 5. Well, I have this idea of the sum or difference property of limits. And what that allows me to do is it allows me to break this up into the sum and difference of the limits themselves. So I can look at just the limit as x approaches 3 of 2x cubed by itself, plus the limit as x approaches 3 of 4x by itself, minus the limit as x approaches 3 of 5 by itself. And so I'm kind of breaking this down. What I'm doing is I'm using the properties from the previous video to ultimately break this down into those singular building blocks that we started with. So the next thing I look at is I look at this particular expression right here and I say, hey, this 2, my scalar multiple property says I can actually take this 2 and move it outside of the limit statement and say this is equal to 2 times the limit as x approaches 3 of x cubed. I can do the same thing with this 4 here. That's a scalar multiple. So I can say plus 4 times the limit as x approaches 3 of x. And then I'm going to leave this one be because that's actually already one of my building blocks from earlier, the limit as x approaches 3 of 5. So now that I've done this, by splitting it up, moving my multiples out, I actually have the building block statements from two videos ago. If I look at the limit as x approaches 3 of x cubed, there's my x to an integer power. I can simply say that's equal to 3 cubed. And then, of course, I have that 2 out in front of it. The same thing is true here. The limit as x approaches 3 of x, we have, if we look at that linear parent function, that whatever x is approaching, the function is also approaching. So the limit as x approaches 3 of x is simply equal to 3. And then, of course, I have the 4 out in front of it, and it's being combined through addition. And then our last building block statement that we went over is the limit as x approaches anything of a constant is just equal to the constant. So the limit as x approaches 3 of 5 is equal to 5. And of course, that's being subtracted. Now then, we can obviously evaluate this. But before we do, let's compare it to our original function. In particular, if I were to substitute 3 in. Well, 2 times 3 cubed, 2x cubed, plus 4 times 3, 4x, minus 5, that's exactly what I get if I look at f of 3. Now then, if we want to know what it is as a value, 3 cubed is 27, times 2 is 54, plus 12 is 66, minus 5. So the limit evaluates to 61. But the really big idea here is that this limit as x approaches 3 of this function, because nothing really weird happened like a lot of the graphs and tables we were looking at in the past, the limit as x approaches 3 of this function was simply equal to f of 3. And so as long as the function is well behaved, we're talking about things like polynomials or functions that are continuous, they don't have a break in them like what we've seen with some of our piecewise functions, you are now free to evaluate a lot of your limits using just direct substitution. So if I want to look at, we're going to look at another example here, the limit as x approaches 2, and I'm going to let this be a rational function, 2x squared plus 3x minus 4, divided by x plus 3. Now then, you've probably had it ingrained from the last few lessons that the rational functions, hey, we might get 0 in the denominator, and then we have to look at some other things. Well, if you take a look, negative 3 is going to give me a 0 in the denominator, but I don't have any issues with plugging 2 into this function. And I could actually go through this very same exercise with this function. I could say the limit as x approaches 2 of this quotient is the limit as x approaches 2 of the numerator divided by the limit as x approaches 2 of the denominator. And then I could split those up into their sums and differences. I could pull out scalar multiples. I could boil it down the same way I did this one. And what I would end up back with is just simply whatever the function is evaluated at 2. Something weird happens at negative 3 because it makes the denominator 0, but nothing weird happens at x equals 2, so I'm free to evaluate this using direct substitution, and I can actually say this limit behaves like this. Now the numerator comes out to be 4 times 2 is 8, plus 6 is 14, minus 4 I get 10 divided by 5. So this limit actually evaluates to 2. And if you want to see that, you're more than welcome to graph it or create a table and watch that limit play out. But the limit as x approaches 2 of that function ends up equaling 2. This is also going to hold true for some of our trig functions. The limit as x approaches pi over 2 of sine of x. Well, if you recall, what our sine of x function looks like. It's a continuous function that just oscillates back and forth between -1 and +1. Nothing weird happens. There's no break in continuity. I don't have anything strange. This is simply equal just to sine of pi over 2, which if you'll recall your major trig values, that's equal to 1. So the limit as x approaches pi over 2 of sine of x is equal to 1. And you can verify that with a graph. You know that the sine graph, I'll just do one period of it right here. But as I approach, so here would be 0, there's your pi. You can already tell from what you know from a graph. As I'm getting close to pi over 2, the function values are getting close to 1. And I was able to tell that this time through just the process of direct substitution. Now then, we also want to look at what happens with a composite function. So let's consider the function g of x equal to x squared minus 16, and it's the square root of that entire expression. So what I have, just to kind of break it down to remind you that this is a composition of functions, I can really say g of x is a composition. I'm going to call them j and k. I can say it's j acting on k of x. So k of x, my inner function, I can define as x squared minus 16. That's the part that's inside of the square root right there. And that means my outer function, j of x, is just simply going to be the square root of x like that. Now then, we mentioned earlier that I would explain how that composition property works. And that's what I'm going to do now, because we want to know what is the limit as x approaches 5 of g of x. Well, what that said was that I can take this limit. If I think of g of x as this composition, I can actually look at the limit as k approaches 5 of the inner value, which is k of x. The limit as x approaches 5 of my inner value x squared minus 16. That's a well-behaved function. I can use direct substitution. Plug in 5, you get 25 minus 16. This particular limit is 9. So if the limit of the inner function is going to 9, then what I really need to look at is the limit as x approaches 9 of my outer function j of x, which was the square root of x. Again, that's a well-behaved function, at least at x equals 9, so it's equal to the square root of 9 which is 3. So I can say the limit as x approaches 5 of g of x is equal to 3. I can take the limit, apply it to the innermost function, and then apply that to the outermost function, and I can work with some composition of functions that way. It also happens that this function's well behaved, and you would get this same value just through direct substitution into this one right here, what we started with. But do understand that when it comes to composition of functions, you can take the limit of the inner function, and then that value take the limit of the outer function, and you'll come up with the correct value.